Okay, can you hear me? My name is Remy, and I want to show you some code. Just one on the code. I claim here this is the second most optimized code in computer science. Let's see what it is. So we're looking for all the tuples x, z, such that there exists some y where x, y is in E and y, z is in R. You probably recognize that this is the relational drawing that Xiaohu just talked to us about. Right. So why do we care so much about this? It's really powerful because it lets us combine data from different sources. It also lets us compose programs from different components. It's also really efficient. Given this one single line of code, the optimizer can automatically parallelize it, make it work over distributed storage, make it fault tolerant, and then make it work over streaming data. It's also beautiful, right? So if you look at any talk videos in our program, you see some really deep and elegant connection between database theory and fine-grained complexity, traditional AI, and also probabilistic inference. So I encourage you to check those out. If we change these two operators a little bit, we replace this with multiply and replace that with plus. I hope you recognize this problem here. Anyone realize what this is? Matrix multiply, right? So this is #1 most optimized program in computer science, right? So as we all know, if you care about physics, if you care about science, if you care about machine learning, you're gonna need this thing. And then in our work, we actually look at the sparse case of this expression, which works over sparse tensors and matrices. And then we were able to port over some of the database optimization techniques to optimize sparse linear algebra. So let's see what else we can do to the expression. So we can replace these two operators with any Samarin times and plus. And then we'll see in a bit what other computation we can express. To make it even more interesting, let's introduce some recursion, right? So here we have the same expression, we have a base case, and then we introduce R also on the left-hand side to make it recursive. So what we have here is just, the base case, we say that E is in R, and in the recursive case, we join together E and R to put in the same relation. So to be a little concrete, if we work in the Boolean Samarin, this tells us if we think of E as a graph, which two vertices are reachable in the graph. So we are computing the transitive closure of the edge relation with this very simple, clean logical definition that you can actually run in these systems called Dialog, including the wonderful system by relational AI. Okay. And then if we replace the Samarin operators with the tropical Samarin, we see that still one on the program, you can find the OPR shortest path in the program. And then if you put it through our optimizer, we're actually able to automatically find Bellman-Ford algorithm to run this efficiently. And then maybe that's too simple of an algorithm, so let's go to one of the most complex ones we can handle. Right. So here's a pretty recent algorithm by Brandes to compute the network centrality of a graph. And then we're able to specify the algorithm in just 10 lines of code. And then the optimizer automatically discovers this pretty recent algorithm, which performs thousands of times faster than the naive computation. And that's all I got. Thank you.
Any questions? Yep. Can you say a little bit about how the optimizer works?
Yes. So the reason we use Samarin rings is that we are able to use the associativity and commutativity of these algebraic properties as rewriting rules. So you basically give us a program, and then we use these algebraic properties to rewrite the program into a different form. And then sometimes that would leverage things like sparsity to make things faster. So that's the gist.
Thanks a lot.